This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, hello, welcome back. I already know all the faces, the same faces that come every lecture every week, so thank you for coming. It's good to see some people are still interested in coming to the lectures. Do we have any questions up to now regarding the project, security, anything? So we move on to a new topic today. We're going to be talking about distribution. Anyone has taken distributed systems, the subject? Are you taking it or have you already? Okay, good. So you're going to help me today with the lecture. Anyone else? No? All right. You don't have to have seen it to understand what we're going to be talking about today, but it'll give you definitely a good perspective of everything that we are discussing. So let's. Oh, okay. They're not supposed to be there. Let's start by defining a distributed system. I know we all know what a distributed system is, right? I'm pretty sure of that. We use them every day, but can anyone put that into words for me? Can anyone define a distributed system? I know we know the reason why I'm asking, like, for you to help me with these definitions is basically because I'm trying to prepare you for the exam. I know for me, at least in my case, I may know a concept really well in my head and I may understand it like really, really well, but when it comes to putting it into words, it's very, very difficult, or explaining it. And this is basically what you guys have to do on your exam. You have to take a concept that you understand in your head and you have to very clearly put it into words for us, so that we can mark you. So take this as an opportunity to practice that skill, because here I can give you direct feedback. In your exam, I will take marks away from you instead. So like, this is a very good example because I know that we know what a distributed system is. It's just that defining it, putting it into words, it's hard. So give it a go. Yes. 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 Perfect. So you said a collection of computers, they are connected together, they share a goal, and they communicate with each other by passing messages. Yeah? Do we agree with that? Anyone has anything else to add? That's perfect. That is even more complete than the definition that I had here. So this is taken from the Distributed Systems book. It's written by Coloris, a very famous distributed systems researcher. So a distributed system is one in which components located at network computers communicate and coordinate their actions only by passing messages. Does this fit the idea of distributed system that you had in your minds? Yeah? And if you think of an example of a distributed system and try to fit it into this definition, it's pretty accurate. So basically, a bunch of computers connected by a network, communicating by passing messages through the network. Simply put. Yeah? So if we try to bring back this definition to enterprise applications, what do we think? Do we think that all enterprise applications are distributed systems? Some of them, none, it depends. What are your thoughts? It depends on the goal of the system. Okay, so we have, it depends on the goal of the system. So some systems, some enterprise applications may be distributed, others may not. Yeah, that's your answer. Anyone else has any other view? Or do we all agree? Because there is nothing explicitly telling us in the definition of enterprise application whether it is or not a distributed system. So we sort of have to analyze based on our understanding of enterprise applications. And I think there's, if you remember the definition and the characteristics of enterprise applications that Eduardo talked to you about, I think in the first lecture, there's a couple of things that are giving us pretty good hints to whether they are not distributed systems. Think about the characteristics of of enterprise applications. Can you remember them? You had to write them in your first report because you have to argue that your project was going to be an enterprise application. Sorry? Consistent. So yes, but it was more concurrent access to the data. That was one of the characteristics of enterprise applications. And what is that telling us in terms of users? If we're going to have concurrent access to the data that the enterprise application is managing, what is that telling us about the users? Is it one user? Is it two users? Multiple users? One at a time? Many at a time? What? Multiple users. So there is no single user enterprise application, is there? They're designed for multiple users. If you just remember to the last lecture, I said that at a minimum we have two different types of users, common end users and then administrators. So we obviously are designing our systems to support multiple users. And because we are also designing our system to support concurrent data access, it means that we're not only supporting multiple users, but we're supporting multiple users accessing the system at the same time. Yes? Doesn't have to be one by one, because otherwise we could have, one application running in one computer and then a queue of users, and then one at a time will access the system. But that is not what we're trying to achieve here. How can we achieve this goal of supporting multiple users? If you think of distributing things or separating things so that they can run on different computers. No, think higher level in terms of components. I cannot think of a different way of achieving this unless we split the client and the server into separate components, so that the client can be deployed on one computer and the server on another computer. And so we can have multiple clients running on different computers, sharing the application that is running on a single server. Does that make sense? Yeah? So we can say that enterprise applications are inherently distributed systems, at least from this perspective. Clients and application servers have to be different components, distributed components. Otherwise, I don't see how we could achieve the multi-user goal. Yes? Obviously, this is not the only case in which we're going to encounter distribution in enterprise applications. If you remember, another property of or characteristic of enterprise applications was that they should integrate with other enterprise applications. And then again, this is another case of distribution. You have two different applications that are communicating with each other. Yeah? So we've made a case. Enterprise applications are distributed systems, at least at the client-server level. We will see now that there are many other cases of distribution in enterprise applications, and that's why we're learning some patterns that are going to help us structure distributed enterprise applications. Any questions? No? All right. So there are different ways in which distributed components of a system can communicate with each other. They're going to communicate with each other by passing messages. That is part of the definition. But there's basically two different paradigms that can be used for that. We have remote invocation, and then we have indirect communication. Direct communication is a sort of asynchronous way of communication. We have things like message queues, publish subscribe systems, and we will talk about this in detail in a couple of weeks because it's quite relevant to enterprise applications. But today we're focusing on enterprise applications that have components distributed that communicate with each other by using remote invocation, yeah, which is the first category or the first message passing paradigm on this slide. Basically, remote invocation is calling or invoking a procedure, a method, a function that lies in a different process, and that process may be in a different machine, yeah? There's different ways of doing remote invocation. The most basic way of doing it is by implementing a request reply protocol. This is as simple as remote invocation gets. Don't get confused by the name, it's actually really simple. All of these methods are based on low-level network primitives like sockets. Has anyone used a socket before to make two programs communicate? Yeah. So you basically establish a channel between two programs and then you can send messages, yeah, through the network. But that is not enough for a client and a server to have a meaningful conversation. They need to have a meaningful conversation so that they can achieve this remote invocation. So that's where the request reply protocol comes into play. Basically, the protocol is telling us that when the client wants to invoke a remote operation on the server, it is going to send a request message to the server, and that request message has a specific format that has been agreed upon beforehand between the client and the server. So the client and the server knows what the contents and the structure of this message, yeah? And then when the server receives this message, it opens the message, it interprets the information in that message, it processes that message by doing some sort of operations, and then when this is done, it's going to send a reply or a response back to the client. And that's another message that again has a structure that has been agreed upon beforehand between the two components. Yeah, does that make sense? There's nothing fancy about this. It's just, so basically, if this is still too abstract for you, just think of HTTP. HTTP is an example of a request reply protocol. Do you see why? Yeah. You have HTTP requests and you have HTTP responses. When the browser wants something from the server, it sends an HTTP request. The server does some sort of processing, and then it sends an HTTP response back to the browser. And the format of the HTTP messages are well defined. The browser knows that structure. The web server knows that structure. So that's all that there is to our request reply protocol. Any questions? That is sort of the basic level of remote invocation. There are frameworks that go above and beyond these, and they're providing a more robust service. So if you've heard of things like remote method invocation, Java RMI, or Corva for remote procedure call, or Enterprise Java Beans, remote EJBs, has anyone heard of any of these terms? Yeah? Anyone else? No? If it's pretty new to you, basically they're going above and beyond, because in this particular case of the request reply protocol, the client knows that the method or the operation that it is invoking is remote. It's somewhere else, right? It's nothing new to the client. The client is creating a request with the purpose of sending it somewhere else. What these frameworks do is that they provide transparency. What do I mean by transparency? If we think of the case of remote method invocation, which is invoking a method in terms of what we know as object-oriented design. So when you say object dot method, and then you pass the arguments. Yeah, so we're invoking a method that's going to be deploying an object that lies on another process. So basically what Java RMI is providing for us is you have an object here, and this object lies in process A, and then you have an object here that lies in process B, so in different processes. And what you can do is you can say, let's call these a name for this thing, an order, and this is a customer. Basically what Java RMI is allowing us to do is from here say order dot add customer, and then some whatever arguments. And this add customer method is actually, sorry, I did it wrong, customer. And if you see here, there's no notion of customer. That customer is not within this process. This customer is part of a different process. But Java RMI is providing the mechanisms for us to do this transparently. So you see how powerful that is? Think of this as your client. Think of this as your server. Instead of sending an HTTP request, you're just invoking a method as if the server was part of the client. Yeah? Yeah? It doesn't matter. They can be in the same or in different machines. The procedure is the same. Yeah, we'll talk a little bit more about that, but they can be on the same machine. Still, the mechanism is the same. Yeah? Yeah? This is just to give you an idea of what frameworks are available for you to use in these particular cases. But obviously, if you have a browser, then HTTP is a standard. Maybe if you had a Java Swing client, you would think of using something like RMI. But anyway. Alright, so regardless of which method you choose to for the communication between your components, a remote invocation is going to look something like this. You have an object A and an object B. They obviously lie on different processes. So what happens is A first has to serialize the request. It has to create that message that it's going to be sending to the remote object. It sends the request over the network. Object B, he serializes the request, so opens the message, interprets whatever information is contained in the message, does some sort of processing, then serializes the result, so creates the response message, sends that message back to object A, and then object A has to deserialize that result. So there's a lot happening here versus a local invocation. A local invocation, we have objects A and B, they're running on the same process, so all the communication is taking place via shared memory. This is the case that you're using in your servers, right? You have a single JVM, a single process, a single server program that you launch, so all the objects can interact with each other using shared memory. Yeah? Does that make sense? So basically what I want you to get from here is that local invocation is extremely fast because it's using shared memory. Remote invocation between two different processes on the same machine is at least an order of magnitude slower than doing this. And remote invocation between two processes on different machines is even slower than two processes on the same machine, yeah? So extremely fast, think of a Ferrari. Extremely slow, think of a horse and carriage. Yeah? And this is basically what's going to be guiding all of the design patterns that we're going to be learning today. Remote invocations are slow, they're expensive, they hurt performance. Yeah? So we want to minimize them as much as we can. Any questions? All right. So based on that, Fowler, which is the author of the book that I hope that you are all reading, is telling us the first law of distributed object design is do not distribute your objects. And he feels so strongly about this that basically in the book he says, sell your grandma if you have to, just to get away from distributing your objects. That is how bad he thinks that is. But obviously we saw already that distribution between some components is inevitable between the client and the server, at least for enterprise applications. They have to be distributed, yeah? Then distribution between some components is desirable, at least at the process level. So for example, you want your web or your application server separate from your database. You don't want to have your database and your application server running on the same process. There's only two ways in which I can think of in which we could do this. Can anyone think of one of them? Having this database and this application server on the same process. How do we even do that? Basically, you implement your own database management system as part of your server. So in all of the code that you're writing right now for your project, you add the code that implements a database management system. Obviously, it doesn't make any sense, it's not feasible, doesn't have any advantages, so we can forget about that. There's another way in which we could have both of these running on the same process. Can you think about it? Has to do with the database, a functionality that databases offer. Probably haven't even heard about them because they're a bit old-fashioned. Stored procedures. Have you heard about stored procedures? No? Yeah. So many years ago, a lot of people used to actually have these two things in the same process by using a functionality that that's offered by databases. It's called stored procedures. So it's basically functions that the database will run for you. Not a good approach to use when we have enterprise applications with really complex business logic. It's very hard to maintain or extend our application if we're putting it in terms of stored procedures. It's just a bunch of functions that the database runs. So obviously we want these to be different components. And then distribution between some components can be avoided. So if you have a web server and an application server, you could have them running on different computers or on different processes, but you could also have them on the same process. Can anyone tell me what is the approach that you're taking for this particular project? You have no application server. You just have a web server, Tomcat, a web container, and then everything is running within that web container, right? So you have no distribution there. But an approach that is very common, especially when you're using enterprise Java Beans, is to have a web container or Tomcat for your presentation layer, and then what we call an EJB container or an application server like JBoss for the enterprise Java Beans or your domain layer. So we're splitting the presentation and the domain layers into different processes. And then what J2E does for you, it manages all the remote communication between your servlets and the enterprise Java Beans. It's providing that transparency for you. From your servlets, you're going to be accessing your remote Java Beans as if they were local objects, but in reality, they're running on a different computer. Yeah? So you may very well encounter this approach when you go out into the industry, because it's fairly common. But obviously, if we can avoid it, we should avoid it. If it's not necessary, don't do it, because then you're adding that extra performance bottleneck of communication. And then distribution between some components should be avoided, even if it means selling your family, according to Fowler. And that is, the objects in the domain layer should never be distributed, or should be avoided at all costs. This is a good general rule, but as everything with software engineering, it doesn't necessarily is the case for every specific scenario that you encounter. Sometimes we can't avoid it for whatever reason, or we could actually benefit from doing it. And that is when you have to take the patterns that we will learn today very seriously, because they're going to help you reduce that performance bottleneck. Yeah? I wonder if anyone is wondering what I'm wondering at this point. So basically what we're advising you to do is have everything in a single computer. Have everything running in a single process so that you have good performance. Right? That's the message that you can take from this. But can you argue with me? Is it something that you think is good? Not good? Does it make sense? Think of Facebook. Do you think Facebook has a single computer or all of its entire application running on a single process? Probably not, right? Because the amount and the number of users is that high that a single computer is not going to be able to keep up with the demand. The amount of CPU and memory and resources that a computer has is not enough to serve millions of users at the same time, right? So obviously, what many of you are thinking right now, well, you need to be able to have different computers. An approach that you could use is distribute your domain logic and put a component on each computer, and then as each of the components gets crowded, you can scale it independently. So we could easily launch here a new delivery component, a new customer, a new invoice, a new order, yeah? As the processor that is running this component struggles to keep up with the demand. Obviously, based on what we learned, this may not be the best approach because these entities are going to be communicating with each other a lot. That's the way that object-oriented design works. And so what we're doing is creating a communication bottleneck, a performance bottleneck with all the communication that is going to be happening between components. So instead of helping performance, we're hurting performance. A better approach is clustering. So instead of splitting the components of your application, you replicate the entire application on multiple computers, yeah? So this is our entire application running on different nodes. So these guys don't have to communicate with each other, perhaps only through a database, and we can add more components as the demand for our application rises. And then we could have something like a load balancer, for example, redirecting requests to different instances of our application. Does that make more sense? Yeah? You're definitely going to encounter this scenario, especially today with cloud computing. We have access to millions of machines on demand. Applications are deployed over the web, so the number of users is really, really high. We need to have a way of keeping up with demand, so this is a very common approach. I'm not saying that it is the best approach and it is the approach that you should always follow. No. It is the one that is most likely to be the best solution, but always consider this approach as well, because for that specific application that you're implementing, this may be the right solution. If you think now with cloud computing, we have cloud native applications emerging, microservice-based applications emerging, and basically what those architectural designs are telling you is do this. Have a lot of different little microservices that communicate with each other, and the benefit is that you can scale them really quick and really easily. But as with everything, there is a trade-off between scalability and performance. So, okay. So, assuming that's for whatever reason we have to distribute things, these are some distribution scenarios that you may encounter. Here we have the browser, the presentation layer on the web server, the domain and the data source layers on the application server, and then we have a database server running MySQL, right? There's nothing too different about that scenario. Your case, the case for your project, you don't have these, you have these two components on this web server, yeah. Scenario number 2, we have an application, it may be an enterprise application that is consuming a web server that is deployed on a different server, yeah? that's another scenario. And then finally we have a swing client that is communicating with the domain layer deployed on server 1. Somehow, or for whatever reason, we've had to split our domain layer in two. So we also have server 2 running another part of the domain layer, and then we have a database server. Yeah? Let's zoom in into this third scenario to have a better understanding of what's going on. We had our swing client and our domain layers. Here, in this domain layer on server 1, we have objects A and B. And domain layer on server 2, we have C, D, and E. Yeah? So the swing client is communicating or is sending requests to object A. So it is invoking methods from this object. And object B is communicating with object C on server 2. Yeah? We're going to say that A and C are objects that are at the distribution boundary. And they are at the distribution boundary because they are the ones that are being accessed by remote objects. If you see B, D, and E, they are local objects because they're only being accessed by objects within the same component on the same process. Yeah? They're the normal ones that we use every day. These are the fancy ones that have to be either Java RMI or a remote EJB or something fancy like that. Yeah? All right. So based on that, we're going to define a local and a remote interface. We're going to talk about local interfaces as those interfaces of local objects. So in this case, B, D, and E all have local interfaces because they're local objects. And local interfaces are going to be fine-grained interfaces because that's how we support high cohesion. That is just a design principle of object-oriented paradigm, yeah? Yes? Do you understand what I mean by fine-grained interface? I'll give you an example, but I want you to try and... How do we design an object in when we're following an object design paradigm? We want, how do we achieve high cohesion for an object? Anyone? Okay, I'll show you the example then, but think about it, the next slide. We have remote interfaces. Remote interfaces are for objects that are at the distribution boundary. So those that are accessed by remote objects. So basically, A and C should have remote interfaces. Yeah? And we want those interfaces to be coarse-grained because we want to minimize the number of remote calls. Maybe at this point you have a better idea what I mean by fine and coarse-grained. Does this give you a much better idea? Fine-grained, customer is a local object, so it has a local interface. It has a fine-grained interface because to get a full name, we get the first name, the middle name, the last name. Because we have 3 different fields in customer. First name, middle name, and last name. Yeah? Contrary to that, we have a customer here that is a remote object. Instead of having this fine-grained interface, we're going to have a coarse-grained interface. So it's a single method that is going to return a bigger chunk of the data rather than small pieces. Any questions? Similar to them? No. But, no. Can you explain me how you think that would be similar? Sort of thinking one of the patterns that we're going to be talking about today. Yeah, keep that in mind. And different cases. One is local, so we have it fine-grained. The other one is remote, so we keep a coarse-grained interface. Yeah? All right. So, it would be simple enough if we could always do that. If we simply have fine-grained interfaces for local objects, coarse-grained interfaces for remote objects. But the thing is that a lot of the times we're going to have objects, like customer in this case, that is a local object because it is accessed by other objects locally, and it is also a remote object because it is being accessed by objects on from a different process. Yeah? So what do we do in this case? Do we keep a fine-grained interface? Do we keep a coarse-grained interface? Do we mix them into one? You know, what should we do in this particular case? Hold the thought because we will answer this question when we see the second pattern. But you see how this is a problem? Yeah? So, two patterns today. Data transfer objects and remote facade. The names are very telling of what these patterns do. So we start with the data transfer object, and this is where your sort of comparison with embedded value will make a lot of sense. If it doesn't, let me know and we will discuss. So this is a data transfer object is simply a special type of object that we are only going to use to transfer data between components. Yeah? Why do we need a special type of object to do this? Why do you think? We're going to be creating or be having a special type of object. We call it a DTO or data transfer object. And the only purpose of that object is to transfer data between two different components, distributed components of an application. So it is the object that I'm going to send to the client, and it is the object that the client is going to send to me. It's going to be encapsulating that data. My question is, why do we need a special type of object for this purpose? Can we use a domain object? Can we use just a return value of a string? Can we use, I don't know, an array? Why do we need a special type of object? Exactly, to minimize the number of communications. Because this object is the one that is going to be bundling together a bunch of data from multiple domain objects so that we can return a lot of things with a single call. Yeah? Is it making sense how it relates to, yeah? Yeah, okay. So remote calls are expensive. We want to transfer more data with each call. We want to return more than a single value with each call. We're going to use a data transfer object for that purpose. Obviously, this is not the only approach you could use. You could have a generic data structure like an array or a dictionary. But again, if you go for that type of approach, for this generic data structure, you don't have strong typing. There is a lot of type casting at the client or the server end, depending who is accessing the object. I'll give you an example of this in a little bit. All right. So a GTO assembles together multiple attributes from multiple objects into a single object that can be then sent over the network. Yeah? It's very simple. It only has the getters and setters and a serialize and deserialize method. I'll talk about this serialize and deserialize method in a moment. Has no behavior, has no logic, and has to be understood by both the client and the server. Yeah? Is it clear? Okay. What is serializing and deserializing? Can anyone define that for me? Exactly. So, for example, in this particular case, it means taking that object or the fields of those objects and putting them into a format that can be sent over the network and can be understood by the server. Yeah? Deserializing is the opposite. So, because DTOs are designed to be sent over the network. They have to be serializable. So the fields should be primitive types, other data transfer objects, or other serializable objects. Anyone has used the serializable interface in Java? No? Well, basically Java can do this for you automatically. If you have two Java programs that are communicating with each other and you want to transfer an object from one program to the other one, you simply have to implement the serializable interface on the object that is going to be transferred, and Java automatically serializes the object for you, sends it across the network, and deserializes it at the other end. But the type of serialization that your DTOs will be capable of doing is going to be dependent on the framework that you're doing, that you're working with. So if you're using something like Java RMI or Enterprise Java Beans, those frameworks do this automatically for you. Don't even have to worry about it. If you're going low level and you have two Java programs that are communicating using a socket, then you're going to have to write the serialization code yourself. Yeah? So here we have an example of the data transfer object. We have two domain objects, a customer with a name and an address that has a street, a suburb, and a postcode. Yeah? And basically, we want to be able to transfer all of this information, or all of the customer information, to a client within a single object. So that's what the customer DTO is going to do. If you see, it has name, street, suburb, and postcode, which is all of this information in one. We need a way of converting data transfer objects to the domain objects and the other way around. So for that, we're going to use an assembler. An assembler is nothing more than a mapper. A mapper from DTO to domain model, from domain model to DTO. So here we have methods like create customer DTO, giving a customer, update customer, create customer. Yeah? Let's have a look at the code. But do we have any questions so far? Our DTO object, as I said, is extremely simple. Field, here it's getters and setters, a serialized method and a deserialized method, if you have to implement this yourself. If the framework is doing it for you, don't even bother having this, okay? So in this case, I'm converting the object into JSON. And you can see how simple it is because I'm using the JSON library from Google, but yeah, that's it all for you. So basically this, it produces a string, a JSON string that contains all of the information of that object, yeah? Deserializing the other way around. From a JSON string, I create a customer DTO. Yes? Any questions? Okay. This is the customer assembler. So here we are creating a customer DTO based on a customer. So all that we have to do is so we get all the information, extract all the information from the customer object. So we get the ID, the name, then we get the address information again from the customer object, the street, the suburb, and the postcode from the address object. Yeah, I'm just extracting information from the domain objects at this point. And then the result, which is our customer DTO, we set all of the properties with the information that we gathered from the domain objects. And that's what we return. Yeah? Any questions? Can I move on? This is another method in the customer assembler. In this case, we're going to update a customer. So we're going to update the domain model based on a DTO. Yep. So basically what we're going to do is create a new customer. We get the ID and the name from the DTO object. Then we create the address domain object. We update the details by retrieving the information from the customer DTO. Yeah. And then we simply tell our customer mapper or data mapper to update the customer that we just created. So the data mapper should go to the database based on the ID, based on the ID of the customer and update the records. This is just one way of doing it. You don't necessarily have to update the database at this point. It depends on the business requirements. Yeah? Any questions? Okay. You have just enough time to finish this. So basically we can have different types of data transfer objects. We can have a single type or multiple types. Multiple types is the case that we just saw. We basically can have a DTO for each request or each use case. So if we are sending information about a customer, we can have a customer DTO. If we're sending information about orders, we can have an order DTO. So let's quickly do an example, assuming that I have an album that has a title. I have an artist. The artist has a name. And then we have track. And the track has a title and length. Yeah? And then we have an album. We're going to say that it can have one artist, and then an album can have multiple tracks. Yeah? So if we were using the multiple types approach, like in the example that I just showed, we would have an album, perhaps, data transfer object. And that object has a title, a name, yeah? The title of the album, the name of the artist, and then it has a list of track DTOs. Yeah, does it make sense? And then we obviously would have something else here. We would have a track DTO with just the information on the track in this particular case. The title and the length. Yeah? That's multiple types. Single type, we basically have a single type of DTO that is going to be used for every use case or for every request in the application. So basically a way in which you would implement this is by having a map that has a string as a key and then an object here. So you see we can use this to store pretty much any type of information that we want with a meaningful key as the string. So in this particular example, our map would our map would look something like this. Title, name, yeah? And then we would have another entry here that would be tracks actually. And then what would I have here? A list of tracks, but I can put an object in there. A list of map. See how messy it can get? And then this map has title and then length. So it can get messy really fast, and there's basically no semantics to it. So when the server is going to go ahead and process this information, you can see how that method is going to be pretty messy. You go through the map and then go through the list and then through the map to access all of the information. Yeah? So DTOs are not that bad when we face scenarios like that. All right, simple compatible with remote facade, which we will talk about next lecture. Bad thing is it has low cohesion. We're bundling a lot of things together that really shouldn't be together, right? But that's the price we're paying for performance. Okay.